as Antoine said, I'm going to talk about superconductivity in the Hubbard model. And I don't really know how to pitch this talk. There are many of the world's experts on this topic here. But on the other hand, talks always need to be to multiple people. So please excuse me if I repeat things that many of you already know. I'm going to talk about work done over many years with a variety of collaborators. The new work that I'll talk about in particular is in collaboration with Hongchen Zhang at Stanford. This is a big topic. I Google searched last night on superconductivity in the Hubbard model and found 330,000 results. I tried to limit it, and I added a modifier, and there were still 94,000 results. I'm obviously not going to review the whole topic. My best attempt at reviewing at least a larger portion of the topic was recently published in a collaborative review with Dana Rovis, Eresberg, and Sri Raghu. Let me start with some ideological statements that I suspect I'm preaching to the choir here, but I think are important. Oh, I should say, for people who are participating by Zoom, you can ask questions by raising your virtual hand, and then your ability to ask a question will be enabled. And anybody here who wants to ask a question, please feel free to interrupt. Right, so what I'm going to talk about is very narrowly focused on trying to obtain reliable results on the Hubbard and TJ models. And so, well, I like to say that the Hubbard model is to highly correlated electron systems, as the Ising model is to statistical mechanics, with the difference that we pretty much know the solution of the Ising model, but the Hubbard model is still a subject of active research. In the context of high temperature superconductivity, which is the context that I will be discussing these results, the high temperature superconductors are very complicated materials. There's a lot going on. It's not even obvious what it's going to mean to have solved the problem of high temperature superconductivity. We can, however, and presumably will eventually solve the problem of high temperature superconductivity in the Hubbard model. And hopefully that will give us some insight into the more physically interesting problem of high temperature superconductivity in real materials. So just to discuss the context in the notion of high temperature superconductivity, this is a sort of composite phase diagram of the hole doped cuprates from a review article that I wrote with this group of co-authors. It's actually not a very good article. It's a triumph of diplomacy that we got this group of people with very strong views to at least agree on some subset of facts. So what are some of the salient things that one would like to understand that this phase diagram presents us with? Well, one is there's the antiferromagnetic insulating parent phase. There's a robust dome of D-wave superconductivity with high transition temperatures. There's a large number of other ordered phases that have similar energy and temperature scales as the superconductivity itself. This is something we've referred to as intertwined orders. Somehow, in some ways, these looked at first like distractions that may be things that you would not want to think about and we would hope would go away, but it's been sufficiently hard to make them go away. And in fact, more and more as people look more and more carefully, they seem to be increasingly ubiquitous. So probably this is part of the problem and something that we would like to understand as well. And then there's a variety of puzzles associated with the normal state, both this strange metal regime and this pseudogap regime that are also not well understood. So these are sort of the broad things that would like to understand from a theoretical perspective, inspired by experiments in the cuprates. Okay, so there are different theoretical methods that are suitable for different sorts of questions. The low temperature ground state properties, especially in the presence of intertwined orders, have possibly very delicate interplay of long-range correlations, which determine the ultimate pattern of broken symmetry. And so this means that even very reasonable and generally reliable approximations can yield answers that are just wrong, in the sense that if they get the balance between two very nearly competing phases wrong, you can give a right description of a wrong phase. By contrast, the strange metal and pseudogap phenomena have relatively high energy scales, characteristic temperatures associated with them. Moreover, it's an empirical fact that in most of this regime, the correlation lengths of at least any orders that we can measure are quite short. So the physics is likely more local, and where approximate treatments that manage to get the big energies in the local physics right can be extremely powerful. And I think I was talking with Antoine this morning. He talks about this, this fact that different methods apply in these different regimes, that one of the goals here is to make a handshake between methods that work here and methods that work here. I won't be talking about that handshake. I'll be talking entirely about methods that work here, and we'll have nothing to say about this class of, in some ways, possibly more important problems, since it involves the high energy physics, but anyway, different set of problems. Okay, so the other thing that we should acknowledge is that the Hubbard model is not a microscopically reasonable model of any actual quantum material, and certainly not of the cuprates. So the sorts of ways we play around, we may not always care whether the model we're looking at is the best possible representation of any particular material. What we're going to try to do is to learn to look at these simple models by what I call controlled approaches, which I'll define in a minute, in order to make at least some confident statements about certain behaviors of these models. And then we can discuss whether we learn anything from that about real materials. So in particular, there are all these approximate approaches that have been developed and have been increasingly, I was just told I'm not supposed to use this word anymore, increasingly sophisticated applications of this. I want to stress that even though I'm not going to be talking about these, this is really what we want for the whole description. We don't want to have to use the unwieldy methods that I'm going to be describing. We want ultimately to be able to have simple approximate methods that we know are reliable. However, what we're going to see is that precisely in this intertwined order regimes, sometimes these make, for just the reasons that I said, wrong predictions. Okay, that I want to stress is not a criticism, that's a statement. Okay, so what am I going to address? As I said, I'm not going to address these questions. What is the nature of the normal state out of which the high temperature superconductors evolve? I'm also not going, I'm going to mention in passing things about the antiferromagnetic insulating parent phase, but as far as I'm concerned, that's a phase that's completely understood and has been understood for a long time. What I'm going to try to get an understanding of is the existence of a robust dome with D-wave high temperature superconductivity and the existence of a large number of intertwined orders. Okay, so that's the strategy. Are there any questions? Okay, good. So now, so there are in particular a couple of sharp questions I would like to ask of the Hubbard model. First place I want to ask, are the circumstances under which high temperature superconductivity exists in the Hubbard model? So high temperature superconductivity to me has in model space a rather precise definition. It means that I want to be in a regime where the interaction strengths are on the order of the bandwidth, which means there are no small parameters in the problem. And therefore, if there is a superconducting transition, it's going to be some number of order 1, which might not be 1, it might be a 10th or a 20th, but some number times the bandwidth. So the question is, does high temperature superconductivity occur in the Hubbard model? And then one other issue is, can we get superconductivity in a lightly doped mod insulator? That is to say, can we find a case where we find superconductivity that persists as the doping concentration goes to 0, and at the same time, this would suggest that maybe we'll find a regime where the superfluid density is parametrically small in proportion to the doping concentration, while the pairing scale is somehow inherited from the insulating phase, so that one will get into this interesting regime, which does seem to be observed in the cuprates, where Tc is of order the superfluid density, and the pairing scale is larger than Tc, and not anything to do with Bose-Einstein condensation. Yeah.
I have a question about the first one. I would be content enough, and this is also suggested by some calculations, that Tc would be proportional to the super exchange rather than the bandwidth, and I would still call it high.
Yes, I agree with you. I mean, so when U over W is of order 1, there's not really, we're talking about numbers of order 1 here. So. Yeah, so we can come back to that. Here I don't have to, the way I've defined it here, I don't think I really have to worry about it. I'll talk about the large U limit, which I think does not superconduct. So then it's really a question of a pretty large U limit. And okay, anyway, I agree with you that probably more likely, in physical terms, it's Tc some number times J is what we're after. So I agree with that. Okay, the Hubbard model. I'm going to typically be talking about the Hubbard model on the square lattice and only with repulsive U. The parameters are going to be the strength of the interaction, the density of holes per site, or X, the density of doped holes per site. And I will allow myself to play around a little with the band structure. For instance, here I've showed turning on a second neighbor hopping. That's my proxy for changing the band structure. Okay, I already said that. And some of the results that I will be talking about are for the Hubbard model, and some are actually for the TJ model, which isn't quite any limit of the Hubbard model, but sort of is. So if you want to convert between Hubbard and TJ results, you can use this approximate relation that U over T is 4T over J. Okay, good. So now I wanted to approach this problem in terms of controlled calculations, and generally controlled calculations require a small parameter. So here's a zero temperature phase diagram for the Hubbard model. I'll be showing this a lot. Here's the non-interacting line. Here's U equals infinity line. Here's doping away from the half-filled case of 1 electron per site. So there are limits of this phase diagram where there are small parameters, and you can hope to get a controlled solution using those small parameters. There's the weak coupling line. There's the strong coupling line. There's light doping. There's dilute electrons. All of these are small parameters that you can hope to use in order to get an understanding of the peripheries of the phase diagram at least. And so I'll spend some time on that, but I want to remind you that this isn't the problem we want to solve. We really want to solve this intermediate coupling problem if we're after high temperature superconductivity. Okay, so in weak coupling, there's a perturbative RG treatment that is, I believe, asymptotically exact. You know, this is an institute that has mathematicians in it, so exact is in the physicist sense, not in the mathematician sense, although I would love some mathematician to try to see if any of this can be put on a halfway rigorous basis. So this RG treatment is mostly the same diagrams as the old Cohn-Luttinger. It's a somewhat different derivation, and the physics that gets emphasized from this approach is quite different from that of Cohn and Luttinger in a way that I'll describe in a minute. And so in particular, Cohn-Luttinger emphasized the existence of a sharp Fermi surface as the essential feature, and that certainly is an essential feature. That's what gives rise to the Cooper instability. But the effective interactions, it turns out, are come from band structure effects that comes from states that are not particularly near the Fermi surface. And so this is quite different physics that comes out of this analysis. And the other thing to say is that except under extremely fine-tuned circumstances, this Cohn-Luttinger-like superconducting instability is the only weak coupling instability there is of the system. There are generically no other weak coupling instabilities. So what comes out of this is an asymptotic expansion for TC. It's ultimately of a BCS form with a dimensionless coupling constant lambda, and lambda has an asymptotic expansion in powers of u, of which the leading order term is u squared. So in terms of magnitude of TC, this is worse than anything you've ever seen. it's not only exponentially small in your small parameter, it's exponentially small in the small parameter squared. Nonetheless, we can calculate at least the first two terms in this asymptotic expansion exactly. That is to say, if you give me the band structure, I can calculate these two coefficients, A and B, exactly. So these follow from properties of the non-interacting system. We can also calculate the symmetry and structure of the gap and the pair wave function in this limit. And just coming back to this distinction with Kohn and Luttinger, if we were in 2 dimensions and had a circular Fermi surface, there is still all the RKKY oscillations that you have that Kohn and Luttinger talked about. Nonetheless, for that problem, this coefficient A is exactly 0. And so any deviation of A from 0 in 2 dimensions is, by definition, a band structure effect. Okay, so here's results for the Hubbard model on various lattices. Mostly, this is just to show you that it can be done. The different lines are the lambda in different symmetry pairing channels. Here, these two are for the square lattice. This one is for no second neighbor hopping. This is for a second neighbor hopping of the sort that people include to mimic the band structure of the whole doped cuprates. In both of these cases, anywhere near half filling, you see a very strong D wave, that is to say x squared minus y squared symmetry pairing, which dominates the physics. For other lattices and other regions of doping, you can get all sorts of interesting things. You can get P wave, you can get D wave, other D wave, you can get F wave, you can get G wave. Okay, so coming back then to the phase diagram of the 2-dimensional Hubbard model, I'm now able to tell you what the phase diagram looks like down here at this edge. This occurs at some rather high doping. There's some first order transition between the dx squared minus y squared and the dxy. Okay, I'm going to focus on smaller values of x, so I'm going to drop that from my future pictures. So we have down here a universal answer that we have dx squared minus y squared wave superconductivity. All right, good. Okay, that's what I just showed you. Okay, now also for only nearest neighbor hopping, there is another non-superconducting instability that occurs due to the perfect nesting of the Fermi surface for only nearest neighbor hopping, that there's an insulating pi-pi spin density wave state that occurs at arbitrarily low doping, and that extends to a strong coupling Niel antiferromagnet with local moments. There's presumably some crossover between these two limits, but as far as we know, no phase transition. So I'm going to drop that. That's the same phase up there. Now, this pi-pi insulator really is a state that's exponentially fine-tuned. There's a scale of doping that one can extract from this, which is exponentially small at small u. So in terms from the small u perspective, this insulating phase is really an anomaly and requires, well, exponentially fine-tuning. There is a regime here, even at weak coupling, that is complicated and I think still not completely understood. Within this regime, there's all sorts of possible other phases that can occur even at weak coupling. There are stripes, which is the solution of the Hartree-Fock equations. There's the possibility of phase separation. There are various other ordered states that have been mooted, and I think it's really not clear exactly what occurs in this corner of the phase diagram. We can ask, how does this phase diagram change if we turn on a very little bit of second neighbor hopping? That spoils the perfect nesting of the Fermi surface, and so it moves the critical value of U, at which we have antiferromagnetic order, up to a finite value. Actually, this moves up rather quickly. This only is logarithmically small in the second neighbor hopping. And presumably then you again have some region here that we don't understand, but now we really don't see any other phases at weak coupling. Good. So that's that side of the phase diagram. So what have we learned? For U small, there are none of many things that we would have liked to see if we wanted to understand the physics of the high temperature superconductors. There's no density waves, no insulating states, no competing orders or spin liquids of any flavor, no non-Fermi liquids, marginal Fermi liquids, starred Fermi liquids, nearly antiferromagnetic Fermi liquids, or even bad Fermi liquids, and there are probably no interesting quantum critical points. Okay, so all of those are things that we would love to have found, but they're just not there at weak coupling, at least not generically. What's generically there is unconventional superconducting ground state with a extremely low TC. Now, if one is bold, one might try to extrapolate the results obtained from weak coupling to intermediate coupling. And so if one did that, one would get a TC that was some number times E Fermi. And there are various ways of doing this extrapolation, all of which, for reasons that aren't all that good, but probably aren't wrong, end up estimating that this number can't be bigger than about 1/10, okay, for what it's worth. And you can make at least reasonably good postdictions of the nature of the superconducting state in many real unconventional superconductors based on this sort of extrapolation from the band structure. Yeah, I think if you can hit the button so that the Zoom people can hear. Yeah.
Go back to this phase diagram. You said there are no quantum critical points. So is that because the green line is first order or red line? Is red line?
So, okay, it's conceivable that there are quantum, I mean, we don't know. So first place at weak coupling, this line doesn't come down to here. Now, it could at the Van Hove point, which is now moved off of here. So it's not that a quantum critical point is impossible, but it doesn't leap out at you. It's not something that has a big effect on the phase diagram.
But I guess the question is that there is just one right here, right? The red dot is.
Yeah, but it's not at weak coupling.
But Steve is living below that.
What?
Well, you can tune it.
You can tune it with T prime. So if T prime is exponentially small, you could bring it exponentially close. And that may be an interesting way, you know, so there may be interesting ways of getting at some of this strong coupling physics by fine tuning your band structure to one of the few places where the generic weak coupling physics breaks down. And I agree that that's a promising thing to do. I haven't succeeded in doing it, but it's, you know, it's a good idea.
But wait, I'm sorry to hold you up, but just to continue,
with that, at a non-zero T prime, there's generically a n at which the Van Hoff singularity touches the first
Right,
order.
and that can also,
So your statement is basically we're just going to stay away from that.
exactly.
Okay.
Or, you know, so, or if you want to look at the physics of quantum critical points or any of these more exotic things from the weak coupling physics, the price you're going to have to pay is you're going to have to fine tune your band structure a lot to one of the places where the generic weak coupling physics doesn't apply. And they exist.
Density, not
What?
Fine tune the density, right?
Both
for any T prime.
For any T prime,
which...
there's a density. I agree. Yes, yes, indeed. Exactly. Good. So anyway, generically, we find superconducting phases at weak coupling. So I'm now going to mention what happens at strong coupling. Here I'm relying on DMRG results that are by now quite old, and I think much better studies can be done. And I would love to stimulate somebody to do better calculations. I'm fairly confident our results are right, because unlike what happens at intermediate coupling, the answers we get seem to be very robust. They don't depend on what we take to be the band structure or how many legs we have of our ladders. So I'm pretty sure our answers are right, but this is a place where better calculations would certainly be welcome. So what we find is actually at some doping an antiferromagnetic insulating phase, and mostly what we find is strong ferromagnetism, no superconductivity at all. So here's a sketch of what we've inferred to be the large U portion of the phase diagram. There's, of course, the antiferromagnetic insulator here. There's a region of two-phase coexistence to a half-metallic ferromagnetic phase, which persists over a broad range of doping.
Can one be a little more quantitative about how large is large? Because my experience with ferromagnetism and other kinds that really requires very...
Yeah, the student left, but we did some estimates, and it seems that U equals 100 is the sort of ballpark for what you need here. So I think this is an interesting limit as a point of principle, but as a practical piece of physics, it's probably not relevant. Okay, but what it does mean is that in some formal sense, we're not going to be able to view the superconducting state that occurs, we hope, at intermediate coupling by adiabatic continuity from the strong coupling limit, whereas we can still hope that we can approach the intermediate coupling problem from weak coupling. So I agree with Antoine again. That's one of the nice things about this field, is that there really are facts and we really can agree on them.
So all this is about the on-site U Hubbard model.
Yeah.
How I don't know, how robust are these numbers and facts to adding 10% of whatever?
So in most, for the weak coupling case, that I can answer. And what happens is that this general story holds, but the balance between the different pairing channels is changed. In particular, the pairing channels that have pair wave functions that vanish not only on site, but on first and second sites are, for instance, favored. So if you like G wave or F wave, you're going to be happy with the nearest neighbor V. You survive to some range of nearest neighbor V without changing things. So the general structure from a large distance is not changed, but but the details can be very sensitively changed by changing the nature of the interactions. Elsewhere, where most of the results that I'm going to quote are numerical, the answer is I don't know. Any other questions? Okay. So the other approach, and I've really already dipped into it, but now I'm going to dip into it more seriously, is to use numerical approaches. And there are many such approaches that have been used. I'm going to be talking about variational methods, and in particular, just this week, two interesting papers using this, which I think is a variational method at the end of the day, but I need to be educated on this. I haven't actually read these papers, just noticed that they appear and have, more or less congruent conclusions to the ones that I'm going to be discussing. What I'm going to do is focus on DMRG results, which are a very powerful variational method. It's got this good feature that you can make it better and better by increasing the bond dimension. On the other hand, you pay the price that you always are stuck with sort of one-dimensional geometries. If you look at a system of width W and length L, you pay exponentially in general as W gets big. So we're typically looking at results on eccentrically shaped clusters. And there are two ways that people have looked at these in order to try to extrapolate results to 2 dimensions. One is to look at W of order L, that is to say maybe L equals twice W or something like that, and compare different sizes and try to extrapolate to L equals infinity. That's trying to keep the geometry as 2-dimensional as possible. The other is to, for each fixed L, first make the system as long as possible to try to figure out what the true thermodynamic phase is of this system viewed as a one-dimensional quantum system, which means it's ultimately some one-dimensional multi-component system where the number of possible low-energy, long-distance behaviors is more or less all understood. And so one can try to get the big enough L that it's clear exactly which CFT is describing the long-distance physics of your system. And that's mostly what the calculations I've been involved with has adopted as a strategy, although both of these strategies are applied and don't seem to give particularly different answers. Good. So there have been many DMRG studies of the Hubbard model. They've produced evidence of various types of orders. They've produced evidence of unidirectional charge density waves, either with or without concomitant spin density waves, and with different wavelengths, either with wavelength 1 over x, which are sort of like the Hartree-Fock stripes, or wavelength more like 1 over 2x, which are these half-filled stripes originally discovered by White and Scalapino. And in fact, other periods of stripes have also been seen. They sometimes see a commensurate lock-in between the favored period of the spin density wave order and the favored period of the charge density wave order, but not always. Sometimes they oscillate at unrelated periods. And at least D-wave superconductivity of one sort or another is also seen. And most recently, people have reported some evidence of antiferromagnetism coexisting with superconductivity. And as I just said, ferromagnetism is seen at large enough U. Now, not everything that you could have imagined is seen. No bidirectional charge density wave order is seen. I have no idea why. Pair density wave order hasn't been seen. I've looked very hard for that. That's very disappointing. No orbital loop order. No d-density wave order. No S-wave superconductivity or spiral spin order or spin nematic order, or I don't know, various things. So it's not that everything in that you could imagine has been seen. And this may or may not be good news if you think that one of these things plays an essential role of the physics of the cuprates, then you might conclude that the Hubbard model or the versions of it that have been studied to date are missing something significant. Or if you think that none of these things are seen or are important, then this is maybe a triumph of the Hubbard model. Okay, so now I'm going to turn to some relatively recent DMRG results. There were a set of papers here starting, I think these papers may be the first of the ones I'm showing here, but there are a variety of these papers looking at that basically the core of it is studies, I think more or less on four-leg ladders. And you might notice that some of these say superconductivity, and one of them very proudly announce absence of superconductivity. I think that most of these calculations involve the Hubbard model with T prime equals 0 and doping of equal to 1/8 or nearly 1/8. And probably there's actually no, as far as I can tell, there's no inconsistency between these different results. What was really important and new in this paper is to declare what I think was a very important finding, which is that the evidence here was that the pure Hubbard model, at least at 1/8 doping, does not superconduct. And to many of us, that was a bit of a surprise, even those of us who had found this in other DMRG calculations. And this is in clear conflict with what came out of some simple approximations. Now, there's a problem with the four-leg Hubbard ladder, or in particular the four-leg Hubbard cylinder. We did an early, very large calculation on this. Many of these are also. And so one of the things is that four-leg cylinder has a very special geometric property, which is that the plaquette perpendicular to the direction of the cylinder is also an elementary plaquette. And so if there's a tendency towards D-wave superconductivity of some sort, it could choose to be this, which in some sense is the only true D-wave superconductor you can get. This is D-wave in the sense that it has a non-trivial transformation property under the symmetry group of the system. So in this case, rotation by 90 degrees about the center of the cylinder. There's the more familiar D-wave-like superconducting state, which has, say, positive pair field on x-directed bonds and negative fields on y-directed bonds. And so there's a lot of issues in interpreting the results on four-leg cylinders that make it well, difficult to make conclusions about two dimensions. I think I'll skip this. So more recently, there's been a number of results on 6-leg cylinders and ladders. There's a work that I did with Hongchen Zhang. There is a paper from the group of Donna Sheng, and there's a paper from White and Scalapino. These all came out within a month or so of each other. They all find charge density wave, that is to say stripe order, and no superconductivity for T prime equals 0 consistent with the conclusions of this absence of superconductivity paper that I cited. They all find some tendency for superconducting correlations to be enhanced by a positive T prime. There are some differences in interpretations of the results between the Sheng and the White papers. You can't make a comparison with our paper because we considered a larger value of T prime than anybody else did. So there's not a direct comparison possible here. Let me tell you why we considered such a large value of T prime. So what we were thinking about was the following thing. If we look at the undoped system with only nearest neighbor antiferromagnetic exchange, we know we're going to get an L state. And if we look at the same model with strong second neighbor antiferromagnetic exchange, we instead get a striped antiferromagnetic state. But what's been known for some time is that in between these, there's a narrow range where there's some form of quantum paramagnet. I think there's still debates going on about exactly what this phase is, whether it's a spin liquid or a valence bond solid, and if it's a spin liquid, whose spin liquid it is. But there's no doubt that there's this intermediate quantum paramagnetic phase. And so we were interested in seeing whether we could have something like an RVB route to high temperature superconductivity, where we could get superconductivity down to arbitrarily low X in a well-doped spin liquid, ideally. So again, we expect these phases dominated by antiferromagnetism to exist everywhere off of the at low doping, off of the antiferromagnetic ordered states. But what we wanted to do is go along here. So since we wanted, that's J prime over J. I was just realizing this. So we have T prime over T, 1 over root 2. So thank you. I just noticed that that was labeled wrong. So this is T prime. This is J prime over J 0.5. And so what we did was we looked at the TJ model with values that might be thought to correspond to U of 12. We looked at dopings 1/18, 1/16, and 1/12. Let me show you what some of the DMRG results look like. Here's the pair field correlator for systems of length 120 and doping 1/12 and 128 and doping 1/16. And this is a log-log plot. So what you're supposed to see is that these superconducting correlations fall with a power law. The power law is close to 1. So that corresponds to a strongly diverging superconducting susceptibility. Here you see the spin correlator, and you see that this falls exponentially. This is the undoped system, which, as I said, is a quantum paramagnet characterized by short-range spin-spin correlations. Here are the 1/12 doped and 1/18 doped system, and these both have slightly longer spin correlation lengths, but ones that are more or less continuously connected to the spin correlation length of the undoped system. here's the spin gap as a function of system size. Here's for the undoped system. Here's for the lightly doped system. So what you can see is that this state has superconducting correlations that are long range, but it inherits sort of as a superconducting gap, the spin gap of the undoped system. Okay, good. So what have we learned up till now? So what I think we've found is that in the Hubbard model, what's really clear is that in the Hubbard model, we do have this phenomenon of intertwined orders. There are many ordered states that are in some extremely delicate dance with each other. And somehow we have fine-tuned something. We've tuned U to be on the order of the bandwidth. So there's some degree of optimal quantum frustration. The system doesn't know whether it wants to order in real space or in momentum space, but it's not highly tuned, and it's only one thing, and that produces this remarkable panoply of different ordered states. So one thing I would like to conclude from the Hubbard model's calculations is that these ordered states really are something we should take seriously in the cuprates. I think that wasn't obvious. It's still not absolutely obvious, but I think this adds credence to that proposition. Yeah, good, I have time. I want to go a little bit further on this idea that superconductivity is best when we dope not into an antiferromagnet, but into a quantum paramagnet. And in particular, although the line of reasoning in the first result that I showed you was an RVB result, which inspired result, which envisaged the quantum paramagnet as being a spin liquid, I think it's the quantum paramagnet probably more than the spin liquid, which is important. And let me present the evidence for that statement. So this is an old idea that a spin liquid is a superconductor waiting to happen, but there were other ideas of how to make a quantum paramagnet that were in many ways still inspired by this spin liquid idea, but that didn't rest on the spin liquid idea. And so inspired by these, what we did was we again looked at the 6-leg cylinder, but now we're going to force the system to have a paramagnetic state, parent state, by looking at a striped Hubbard model. So what's a striped Hubbard model? It means that I'm going to have the hoppings in the x direction be 1, and the hoppings in the y direction be 1 plus something and 1 minus something. So in the limit that dt is equal to 1, I have just decoupled 2-leg ladders. In the limit that dt equals 0, I just have our old friend, the pure nearest neighbor Hubbard model. So at small dt, so here, whoop. Right, so at small dt, it's the same as dt equals 0. We're going to have a Niel antiferromagnet at 0 doping. But at dt equals 1, we have a system that consists of decoupled 2-leg ladders. And so the individual 2-leg ladders, when they're doped, are known from very extensive DMRG work to form Luther-Emery liquids. And on the undoped system, the striped antiferromagnet has a quantum paramagnetic phase and a phase transition between these somewhere here. What Eduardo Fratkin and Enrico Aragoni and I did was to analyze what happens as you move off of this top of the phase diagram. And what we found was that in some range of doping, you form a superconducting state, and in some other range of doping, you form a charge density wave state. Actually, it's a checkerboard charge density wave state, so it's not one that adiabatically continues to the charge density wave state that's seen at small dt. So we decided to explore this by DMRG. So here, so sorry, here. Yeah, so both of these are spin gapped. So remember, this is for small dt. So this is basically a 2kF charge density wave along each ladder, but then pi phase shifted as you go from one ladder to the next. So you have a charge density wave like this, and then it favors a pi phase shift from one ladder. If you just do second order perturbation theory in the hopping, you get that it favors a pi phase shift from one to the next. It's an incommensurate charge density wave, yes. Okay, so here's the, can I go 5 more minutes? Is that okay? Okay, so here's the sorts of results that we get. Here's the pair field correlator. This is for dt equals 0. This is just the nearest neighbor Hubbard model. So again, you can see that the superconducting correlations drop like a stone. And here we have a dt of 0.3. And well, you can see here that the superconducting correlations at, say, 16 lattice sites has been raised by 5 orders of magnitude. It's a really big effect. And this correlation is falling like a power law with distance. This is the y-directed bonds. This is the x-directed bonds. So this really is a D-wave superconductor, D-wave-like. Again, the exponent that we get for the fall off of these is something around 1. This is the spin correlations, which fall exponentially with distance, with actually rather short correlation lengths. So presumably, there's again this region of doped antiferromagnet that I'm not prepared to say much about, but what we found is that there is a region here which corresponds to a doped quantum paramagnet in which we find D-wave-like superconductivity. What did I do? Okay, so this is my last slide. So here's what I want to conclude. First place, there are intertwined orders. That makes the theory of the low temperature physics intrinsically difficult. Which, in part may be a reason to stay away from it. For U of order 8, strong enough antiferromagnetic correlations tend not to lead to superconductivity, but rather lead to density wave order of some sort. But that, on the other hand, by introducing some form of frustration to make the system look more like a doped quantum paramagnet, it is possible to achieve high temperature superconductivity. I will mention one thing that I didn't put on this slide, which damps my enthusiasm a little bit, which is, at least in the case of the doped spin liquid, the sign of T prime matters. So for the undoped system, all that comes in is T prime squared. So both for T prime positive and T prime negative, we're more or less doping exactly the same phase. But for T prime positive, which is not the sign preferred for the whole doped cuprates, we find this very strong superconductivity. For T prime negative, we don't. Okay, so, well, I'm not exactly sure. We got discouraged, or rather, since I don't do any of the calculations, Heng Chen got discouraged. So we definitely did not see superconducting correlations. I can't tell you what we actually find. It's something that is on the agenda, and as soon as I can get his attention, I'll be able to tell you. But that's embarrassing. Okay. Yeah. So at any rate, I think this idea of a doped paramagnet has at least some of the appeals that are generic that came from the idea of a doped RVB state. All right, so let's see. So here's what I hope that we see, that the Hubbard model has sort of the same parent antiferromagnetic ordered insulating state. It can sometimes have a D-wave high temperature superconducting dome. It very robustly has a large number of intertwined orders, and that doping a quantum paramagnet is a good way to get a high temperature superconductor. Okay, good.
Okay, thank you so much, Steve. So let's see if there are questions from Zoom. I can't see any in the chat right now. So any questions from the audience? Oh, lots of questions. Okay, so maybe, I don't know, let's start with Shiv.
Thank you, Steve. So on the T prime inducing or enhancing superconducting order, do we know what gets suppressed? You know, which of the intertwined orders, you know, do what? Is there some insight on what might be priming mechanism?
So I don't have any insight. It's, I mean, what seems to happen is the charge density wave order gets smaller. So it is some sort of competition between superconductivity and charge density wave, but why positive T prime destabilizes charge density wave and negative T prime stabilizes charge density wave is something I can tell you rigorously that I don't understand it. But it seems to be a very generally observed fact.
Describing the cuprates, how important is disorder going to be in adding to all these computations? I mean, you obviously thought about that a lot. The separation between the antiferromagnetic and the superconducting phase.
Yeah, I mean, yeah. Yeah, so I think disorder is certainly important in the cuprates. You know, people have now worked for 35 years to make the best possible, but you know, it's an alloy, so even if it's perfect, it's disordered, and they're far from perfect. So it's certain that much of the phenomena that we see are dominated, or at least are altered by disorder. I don't know exactly, you know, so okay, I think that statement's clear. What I hope is that the broad features that I described are things that I mean, different cuprates, for instance, have very different types of and magnitudes of disorder. So when you see things across multiple cuprates, doesn't mean that disorder isn't playing a role, but at least I think it gives you confidence that there is an underlying piece of physics that is disorder free. But I suspect that many, many more things than people like to think are dominated by disorder.
Steve, I mean, isn't it a fair statement to say that, okay, disorder certainly affects the balance between, the very delicate energy balance between different competing states.
Yeah.
But if you move to higher temperature crossovers, they are more general.
Yeah, I think that's right. Right. So the very thing that gives theory conniptions here, that you have all these states close to each other, actually gives the materials conniptions also. And all sorts of little details can tip the balance one way or another.
Okay, now is a question from Subir and then Alex.
Well, so none of the calculations you described describe the mechanism of high temperature superconductivity in the real world. So I'm wondering if you can speculate what's going on. Are we supposed to think that maybe the fluctuating CDWs are important for getting a high TC, or phonons have to be added? Or what?
So the trouble with that question is that I have too many answers that I believe in passionately that are mutually contradictory.
What about the good old super exchange?
No, so in some sense, the doped quantum paramagnet is saying that it's being driven by super exchange. So one thing that's I think in common between the weak coupling mechanism and the mechanism of a doped quantum paramagnet is that it's not like BCS that there's an exchange of some well-defined boson, that it's some short distance physics. In the case of the weak coupling, it's some particle hole susceptibility that you get from integrating over the whole band. In the case of the doped antiferromagnet, it's presumably due to short range antiferromagnetic correlations. So as you say, it's due to super exchange. So I think that that's probably the main mechanism, but there are certainly more things going on. One of my favorite ideas is that pneumatic fluctuations are good at enhancing superconductivity if you already have a basic mechanism. Charge density. I have a harder time imagining that charge density wave fluctuations are driving things, but
Well, I was referring to your calculation. So that you find modulated
yeah.
That had a highest PC at some intermediate modulation.
Right.
So I was wondering, is that what you're proposing is important at the end? Or some fluctuating group?
Yeah. So that's certainly, I think that's so as I said, I have mutually contradicting ideas, but that's, I think, the idea that I find most promising. And there are other patterns. Unfortunately, I don't know how to do calculations in the presence of fluctuating charge density wave or something like that. If I did, that would be fine. But I know that there are some patterns of inhomogeneity, ordered inhomogeneity that enhance superconductivity, and many that don't. So again, there's not a simple one sentence answer to that. So maybe things that favor quantum paramagnets. So if you look at the undoped system and try to find something that has correlations that look as superconducting as possible in the insulating phase, that doping those will be a good route.
So we had Alex feedback and then Alex.
I want to turn on the microphone. Yeah, I want to ask.
Hello. So how much do you see it necessary to dope a quantum paramagnet as opposed to an antiferromagnetic host state to get superconductivity? Or another way to phrase this, do you think like that spin order somehow destroys the UF superconductivity?
So, it doesn't rise to the level of a theorem, certainly, but if you look at least the DMRG results, I mean, I think there's no doubt in my mind that short-range antiferromagnetic correlations are, at the end of the day, essential to high-temperature superconductivity. But anywhere where you have reasonably long-range antiferromagnetic correlations, it seems to be bad for superconductivity. You could imagine various reasons for this, but at least I think that is a correct statement about at least most of the numerical data. Do you agree with that?
I think so. I think you want the short range.
Yeah, I agree with that. Yeah.
So this is all sort of along the same lines. So you emphasize the interest in doping quantum paramagnets, which are more frustrated systems. So does that mean we should all be studying triangular and Casimir lattices instead?
I should study it.
So yeah. So I mean.
No, but I mean that in synthesizing them.
Yeah. Yeah. Well, so my colleague Young Lee has a nice Kagame paramagnet, which probably even has a pretty big spin gap, although I guess that's still controversial. Unfortunately, can't dope it. Yeah. So yes. Yeah. 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 So you're all trying to push me into saying things that
But really, I'm just trying to get a sense of your thinking on
yeah.
this subject.
So the triangular lattice by itself presumably orders antiferromagnetically. So that's yeah. So when you put on second neighbor hopping or something. Yeah. 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 So I think so. Okay. So I think so let me try to make a precise statement. So I think that the fact that when we dope into the quantum paramagnet with positive T prime, we get a high temperature superconductors is very encouraging. It says that a quantum paramagnet is a good place to look for a doped superconductor. On the other hand, the fact that when we do it with T prime negative, we don't find a superconductor means that it's not a promise. And in particular, some years ago, we looked at doping a Kagame antiferromagnet, and we found an exotic phase of matter. We found a Wigner crystal star. I'm taking Subir's notation. We found a Wigner crystal of holons. So it was a state that requires fractionalization, but it was absolutely the most boring possible starred state you could get. And that, unfortunately, I think follows a more general principle, which is Murphy's law.
Okay, more questions. Yeah, go.
Steve, can I ask one question? I think you already answered part of it, but let's say we started from this T prime equal to 0, right? There are some insulating stripes and charge order, wavelengths are twice of the speeds are twice of the wavelengths. So then you turn on the T prime, right? Or positive T prime, you're saying that it's a short connected somehow positive charge order. So how about the negative T prime? What is the effect of the negative T prime on the period of the scale and charge order?
So I don't remember. So I have a paper where we did this for the TJ model, where we had both T prime and J prime, and it was all on 4-leg cylinders. So I don't, in retrospect, that was unfortunate. I don't know how many of the things we were seeing were special to the 4-leg cylinder. I have some table there. We found all sorts of different ordering tendencies as we changed these. at the time, I couldn't make any sense of them. I could just make statements that in different regions we saw different things. So, so it's a really good question, but I don't have even a crude intuitive answer to it.